Hello, Professor Chan. Today I'm going to be talking to you about my metal complex, which is a ferrous heme. Oh, to start off, I'd like to talk to you about, no, I'm going to redo that. Hello, Professor Chan. Today I'm going to be talking to you about my metal complex, which is a ferrous heme. To start off, I'd like to give a couple of reasons of why I chose this molecule. First, I'm interested in biochemistry, and as you likely know, hemes are present in biological systems. They're rather prevalent in proteins. Additionally, I think porphyrins are interesting. I don't know much about them, but I like their highly symmetric nature and their polydentate feature. I think that's cool, and I want to learn more about it. So as for the complex itself, it is an iron bound to a tetradentate chelating ligand called porphyrin, which is right here. And then oxygen is going to reversibly bind to this upper axial position right here. This particular figure is from the paper, and as you can tell, it's rather blurry, so I included this much clearer image I found on the internet. This image, however, does include the histidine residue that binds the heme to the protein. However, because it doesn't participate in the chemistry, I'm going to be ignoring it for this case. So there's two versions of this heme that I'm going to be talking about in this presentation. We have our just ferrous heme, no dioxygen bound, and then the dioxygen bound version on this side. To talk a little bit about the geometry, this porphyrin region is going to be square planar. The sp2 hybridized carbons of this aromatic ring make the complex flat, and it has a coordination number of 4 towards this metal. On the other hand, the dioxygen-bound version is going to be square pyramidal, which is basically the same thing. We have this flat porphyrin region in the same plane, and then oxygen exists right above it. As for symmetry elements, this is a highly symmetric complex. It is going to have a D4H symmetry, or this ferrous heme version. It's going to have that 4-fold rotation axis as well as 4 mirror planes. It additionally has an inversion center right here, as well as a horizontal mirror plane that goes through the porphyrin itself. For the dioxygen-bound version, the symmetry elements are all the same except for that horizontal mirror plane, giving it a D4 designation. A quick note is I am treating this dioxygen here like it is in this figure as just a singular point and not this bent configuration, which would clearly influence the symmetry. And now to talk a little bit about the electronic characteristics. First off, the number of d electrons. The ferrous heme is going to have 60 electrons. This is because porphyrin is an L2X2 ligand, so it's going to have a charge of -2 when on its own, when not metal bound. So in order for the entire complex to be neutral, the iron is going to have an oxidation state of 2. And because it's a group 8 element, 8 minus 2 gives us 60 electrons. And then this changes. We remove 1d electron once dioxygen binds, or dioxygen is going to oxidize the complex. And it's not shown in this particular figure, but the dioxygen becomes a superoxide radical by taking that 1 electron. And the iron, that's supposed to be a 3, goes from an oxidation state of 2 to 3. And that gives us 5d electrons. And now to discuss the spin state. There are 2 characteristics of the system that are going to give rise to its spin state. The first one being its geometry. The molecule is going to be square planar, or square pyramidal for this one. And that square planar geometry is going to put this d orbital in the plane of the porphyrin ligand, which is going to make binding very high energy. So we're going to have a large spin splitting energy because of it. Another feature that makes this spin splitting energy high is the nature of these nitrogens that bind to the metal. They are strong field ligands, meaning that the entire porphyrin ligand is going to be a strong field ligand. So in combination of the strong field ligand as well as the square planar geometry is going to give us a large spin splitting energy and therefore make it a low spin complex. If we were to place these electrons into this diagram right here, they'd be located 1, 2, 3, 4, 5, 6, or 5. Simply, we're just not putting electrons up here because it's just too big of an energy gap. A quick note I would like to make is in my research for this, it seems that porphyrin hemes are much more complicated when it comes to spin state than I initially thought. It seems that these molecules can exist in multiple different spin states. It can be in a low or high, as well as an intermediate state and a superposition of those. And which spin state the molecule is in, according to this Nature article, depends on both what axial ligand is present, or ligands, as well as light. For this paper specifically, we noticed that if we take these axial ligands and we switch them out to ones that are rather similar, we change the spin state from a quantum superposition of intermediate and high to just high spin. I know this isn't exactly relevant to my complex because this is a different complex. I just want to point out that spin state for porphyrin hemes is a little bit complicated, and I don't want to say that my molecule, is always low spin. Now back to my particular heme. What are the applications of it? Why is it important? It has what's called dioxygenase activity, meaning it can donate 4 electrons using the whole reduction potential of the dioxygen to whatever substrate, and in this case is going to be tryptophan, which is involved in an important biosynthetic pathway to make this molecule down here, which you may recognize as nicotinamide adenine dinucleotide, or more simply, NAD, which needs no description. It is absolutely integral in biological systems, and because of its importance, this heme is very important. Thank you very much.